Okay, so in this session, we're going to revise Unit 1 in IGCSE Physics. This works for Cambridge and Excel, by the way. I often just use Cambridge, but this works for Cambridge and Excel. They're almost identical syllabuses and curriculums, so it doesn't matter. This is for 2023 because the syllabus has changed in 2023, right? So this is the first unit, General Physics and Mechanics. We'll first start by talking about the update. And every time we revise, we'll talk about the update of the syllabus that was updated this year, 2023. There are certain topics that have been removed, certain topics that have been added. And in Unit 1, General Physics, the primary thing that has been removed is pressure. Not all of it, just the barometer and the manometer. So if you're watching any of the older videos, or if you're studying through older past papers, if you see any mention of a YouTube manometer like this, or a barometer that looks like this, these have been removed from the curriculum for Unit 1. All right, very good. There's nothing that's been added to the first unit that's new. So let's get started. One more point to point out, yeah. Pure IG students, this is for a full IGCSE syllabus, but if you ever see this symbol on something that I'm explaining, it'll either be at the top of this page or to the side next to a specific rule or anything. This is the extended version of the syllabus for the full IG. Year 9 students will not need to study this. Core students will not need to study this, but اسمعوها nonetheless, just listen to it nonetheless. Why? Because it'll help you understand stuff better. It actually gives you a better idea, with the exception of, in this particular unit, the unit of momentum, the chapter of momentum. This is a completely different topic, which you have not touched at all. You can safely skip that part as we're explaining things. Now, in hindsight, I should have probably pushed it to the very end of the video, but يلا مش مشكلة. Let's get started. So what are we studying today? In Unit 1, it's very important to keep in mind what chapters we have and what things we're going to discuss and study. There's measurements and density, so mass, volume, like how do we measure these things, how do we calculate density, and so on. Speed and acceleration, very important topic, very common topic as well. How do you calculate speed, speed time graphs, distance time graphs, acceleration, and so on. Introduction to forces, as in the different types of forces that we have, like friction and weight and air resistance in their details, and how we calculate resultant forces. Hooke's law, which is just springs. So when you apply a force on a spring, it causes it to stretch, and the rules behind that. Newton's laws of motion, which you probably are familiar with when it comes to if you apply a force on an object, it will either accelerate or decelerate or change direction. But if the force is zero, it stays at rest. It's a very common thing, along with other examples of motion. Momentum, this is only for the extended students. Pressure, force over area. Moments, which is defined as the turning effect of a force. And energy, work, and power. So kinetic energy, gravitational potential energy, chemical, and so on. And we'll finish this up. This is a continuation of energy, work, and power, but sources of energy which involve power stations and how we generate electricity. Let's start with the first chapter. Let's talk about measurements. First, you have different quantities. You should be familiar with all of them. These are the important quantities right now: length, time, and mass. They're measured in what we call an SI unit, which is short for Système International. And forgive my butchering of the French language and pronunciation, but it basically means international system of units, standard units for everything. The length is in meters, time is in seconds, mass is in kilograms. Temperature and electric current are in Kelvin and ampere, but these are in Unit 2 and Unit 4. We'll discuss the difference between Kelvin and a Celsius next time, or like later. There are lots of prefixes when it comes to these units. The three most common prefixes are kilo, so 1 kilometer, for example, is 1,000 meters. Centi, which is divided by 100, so 2 centimeters is 0.02 meters. Do you see what I did? I divided by 100. And milli, so let's say you have a time of 35 milliseconds. So you divide by 1,000, by 0.035 seconds. You need to know how these prefixes work. All right. There are other prefixes as well, like mega, which is very rare, but that is times 1,000,000 or times 1,000,000 essentially. And micro, which is divided by 1,000,000. But to be honest, they're very rare. They've only ever showed up like once or twice in the past papers before, and that's for extended students too, not course students. So we're going to move on from prefixes and actually start talking about something important. You have many different quantities that you should be able to measure. We'll focus on the measuring instruments and measuring techniques that he loves to ask you about, whether it's in a multiple choice question or in paper 3 or 4 or in paper 6. The pendulum, or the period of an oscillation. The time of one oscillation, as in when the object or like a pendulum goes back and forth, is called a period. To measure the time of one oscillation accurately, you need to measure the time of, let's say, 10 oscillations. So let's say this is 3.43 seconds, okay, for example, but this is not really 3.43. This is 3 minutes, 43 seconds, and 0.75. But then you divide it by the number of oscillations. So the way you get the period is by taking the total time of 10, 20, 30 oscillations, and you divide it by the number of oscillations. Most common questions use either 10 or 20 oscillations. Then, what about mass? Mass is measured with a balance. It's not really that hard, but you have different types of balances. A top hand balance, where you just put stuff on it and it just gives you the reading. A spring balance, where you hang something on it and it stretches to give you the reading. This is also what we call a Newton meter, because it can help us measure forces or weight. Like we can attach it to something and pull it, and this gives me the value of the force. And finally, the beam balance. It has many different shapes, but the basic concept is this. You have two trays, you put an object on one side and you put a load on the other side, and you compare them. This is very good for comparing things. It's not very good for measuring things though, Sarah. Then, how do you measure the mass of a liquid? That's a technique that you need to understand. The problem with measuring the mass of a liquid is that liquids have mass and their containers also have mass. So for example, here, this is an empty measuring cylinder with a mass of 200 grams. If you only want the mass of the liquid, you'll subtract these two values from each other. 250 minus 200, which is 50 grams. Just 50 grams. So this gives me 50. So mass of the full container minus the mass of the empty container gives you the mass of the liquid. Very good. Next, let's talk about length. We have 3 measuring instruments for length. Actually, 4, honestly, but 3 at least here. A meter rule. This is very good for distances up to 1 meter. So if an object is up to 1 meter long, so about this big, yeah, you can just use a ruler. Just mention rule or ruler, and that's fine. If you have any longer distances, 2, 3, 5, 10, 100 meters, 200 meters, we use what we call a measuring tape or a tape measure. This is really good for very long distances. And if you want to measure very thin objects, like a thickness of a sheet of paper, or the diameter of a wire, or the thickness of a coin, like these are very common questions, you use a micrometer. You don't know, you do not need to know how to use these instruments. You just need to know which instrument do I use when. That's all. However, there are a couple of techniques that you need to keep in mind. The first of which is, how do you get the thickness of a sheet of paper if you don't have a micrometer? Like if you do not have this, and I only give you a ruler, how do you measure the thickness of a sheet of paper? Well, you get your full stack of papers, like if you get your entire book, and then you measure the thickness of all of these stacks of paper at the same time. So let's say you have 100 sheets of paper. You measure the thickness of all of these, and it is about 2 centimeters. Then the thickness of one sheet is 2 centimeters divided by 100 sheets, which gives you 0.02 centimeters. All right? Very good. Finally, how do you get the diameter of a ball? The problem with spherical objects in general, like or circular objects, is that they don't have an edge. So if you put them next to a ruler, your eyes can't really extend this virtual line in the air and get the value accurately. You will almost always get this value wrong. Not completely, but slightly wrong. The way we measure any spherical or round object, the diameter of which at least, is to put it between two flat blocks. Blocks of wood, blocks of metal, blocks of plastic, choose whatever blocks you want. Just stick the object between, between these two blocks. Check the length here, check the value of the length at the first block, check the value of the length at the next block, and find the size of this gap. So what's the diameter of this ball? It's going to be about 2 centimeters. Very good. So that's how you measure thickness or length. These are just special techniques. Finally, when it comes to volume, it honestly depends. If you're measuring the volume of a regular solid, like this cuboid, this box over here, it's simply length times width times height. Again, the volume is length times width times height. Not a problem, right? No problems at all. But keep in mind, the general rule that we use to measure volume or calculate volume of a regular shape is the area of its base times height. So when you say length and width, you're actually getting this. When you say length times width, you're actually getting this. All right? So that's the area of the base times height. Times height. This works with a cylinder, by the way. If I tell you, hey, the cross-sectional area of this cylinder is 10 centimeters squared, and the height of this object is 2 centimeters. What's the volume of this cylinder? So it's 10 times 2, which is 20 centimeter cubed. And that's the unit of measurement of volume. So meter or centimeter cubed. If you're measuring the volume of a liquid, just use a measuring cylinder. This also works with anything that flows like a liquid. Think sand, sugar, rice, like anything that flows, you can get an approximate volume of that as well using the cylinder. But if you want the volume of an irregular solid object, think your keys, for example. They're an irregular shape. You cannot calculate their volume using irregular rules. So what do? We get the volume here. This value should be about, let's say, 50, 60, 70, 75. That's your initial volume of the water. Put some water in a cylinder, and then slowly and gently drop the object into the water so you avoid splashing. So what will this value be? So that's 100, 110, 120, 125. The difference between these two readings is going to be the volume of this rock. So the difference between the two, so 125 minus 75 is 50. Is 50. Very good. So how do you get the volume of an irregular solid? Pour some water in a measuring cylinder, measure the initial volume, put the object in, measure the second volume, calculate the difference between the two values. Next. Any of these measurements could involve a small amount of error. Like, there's always a little bit of a mistake. But there are 3 mistakes that you must keep in mind. There's zero error, which is when the instrument doesn't start at 0 for any reason. Like, again, maybe you made a mistake, maybe you broke the ruler, maybe it's your favorite ruler from when you were 3 years old and you don't want to let it go because it has a picture of Iron Man on it or something. I'm not going to judge. But how do you measure the length of this object? You take the initial reading, so this is 5.2. And then you take the final reading, in this case it's 8.1, and you calculate the difference between these two ends. So 8.1 minus 5.2, this should give you 2.9 centimeters, obviously, because the ruler is in centimeters. Very good. Parallax error. That's when you don't look at something properly. You're supposed to look at an instrument perpendicular to the scale. So you're supposed to hold this ruler and look like this, perpendicular to it. But you're not supposed to look at it above or below it at an angle. That's called parallax. You looking at a different angle to where the object surface actually is called parallax, and that's called a parallax error. So what's the parallax error about? So what's the parallax error? This is, you're not looking right. How do you fix it? By looking perpendicular to the scale. By looking perpendicular to the scale. Good? Very good. Next. The meniscus error. Now, this is not very common, but you will see it a lot in paper 6, by the way, and sometimes in paper 2, like he enjoys that. The surface of the liquid is never properly flat, like this. No, it's not straight, it's not horizontal. The edge of the liquid always, climbs up the container it's in. You might ask, what's the problem? So what? What's the problem? There is no problem. There is. If you were to look perpendicular to the measuring cylinder to avoid parallax error, like you should, you'll end up seeing two readings that are the value. So you're going to see a very thick surface, and you won't be exactly sure which one is it, the upper surface or the lower surface, because of the curvature of the water. So between 40, in this case, this is going to be 40 km, 46, and this is 48, because every square or every division here is 2 centimeters squared, cubed, I mean. Which value is correct? What do you guys think? 46 or 48? 46, thank you. You look at the bottom of the meniscus. We look at what we call the bottom of the meniscus, not the top, because the top is just a drop of water. And finally, oops, I have to clear the board. Let's talk about density. Density is quite simple. It's just mass over volume. It's literally defined as the mass per unit volume of a substance, mass over volume. The more dense an object is, the smaller and heavier it'll be. Think metals. The less dense an object is, the bigger but lighter it'll be. So this could be a 10 kilogram dumbbell, whereas this could be a half a kilogram balloon. So the more dense something is, the more mass it'll have and the smaller the volume. The less dense it is, the less mass it'll have and the larger the volume. Okay. The equation is just mass over volume. This is the symbol that we use for density. We're going to use it later. And this is mass and this is a volume. None of this is actually challenging or difficult. Now, the units in questions could either be kilogram per meter cubed or grams per centimeter cubed. It depends on the question. Just be careful when you're calculating density. I have 3 things to point out. Number 1, density affects whether or not objects sink or float. So if you see an object in water and that object is floating, it's less dense than the liquid itself. And if the density of the liquid is 1,000 kilogram per meter cubed, that's the density of water, for example, then this object that's floating has to be less than 1,000. It could be 900, could be 800, could be anything. And I'm not talking about weight, and I'm not talking about mass, I'm talking about its density. And if you have an object that has sunk into this water, this is more dense than the liquid. So it's more than 1,000. Could be 1,010, could be 2,000, could be 3,000. I don't know, but it's more than 1,000. It's more than the density of the liquid. Point number 2. Same material means same density. So if an object, or you're comparing objects of the same material, then they have the same density. The only thing that can affect density is temperature or heat. The higher the temperature of an object, the less dense it will become, because as we'll study or revise in Unit 2 in thermophysics, when you heat something, its volume increases, but the mass stays the same, so the density is affected. That's what causes convection. But keep that in mind. The only thing that affects density is volume. is temperature. Okay, very good. Yeah. Do you have any questions so far? Nothing? Good. Moving on. So calculate this example very quickly. 500-gram block. It has a length of 10, width 2, and a height of 5, for example. What's density? This is quite simply mass over volume. So that's 500 over 10 times 2 times 5. So 500 over 10 times 2 times 5. This gives you an answer of 5. But wait, 5 what? If this is in grams and this is in centimeters, and centimeters and centimeters, you have 5 grams per centimeter cubed. Moving on. Oops. Let's talk about speed and acceleration. Very quickly. What is speed? Distance over time. Speed is nothing more than distance over time. It's either meters per second or kilometers per hour, depending on the question. Careful with the units. If I ask you to calculate average speed, it's the same thing. It's distance over time. It's just total distance over total time. So solving this example very quickly, speed is distance over time. Oh, we need to read it first. A car travels 100 kilometers. That's great. We have the distance. The highest speed is 90 and the lowest speed is 30. This is a question from paper 2 or paper 1, multiple choice. The journey takes 2 hours. What's the average speed? I don't care about the values of speed that he's given me. He's given me distance and he's given me the total time. So it's just distance over time. So 50 kilometers per hour. Next. Now, before we move on, some quantities that we study will be scalars. Some of them will be vectors. Scalars are quantities that have only magnitude, like length, time, and mass and such. And vectors have both magnitude and direction. Why are we mentioning this here? Because speed is a scalar quantity. We only care about the value. However, if an object is moving and you want to add to its speed, like in meters per second or kilometers per hour, its direction, we call it velocity. This is a vector because it is described with the value and the direction. So it's 10 meters per second. No, it's 10 meters per second to the right, for example. For most questions, this won't matter too much. It will matter when we talk about forces. So, next up. Let's talk about acceleration. Acceleration is defined as the change in velocity or change in speed over time, or rate of change in speed. It's calculated using change in velocity over time. We often write this down as delta v over t, although sometimes it will be written as v minus u over t. The unit of measurement of acceleration is meters per second squared. Now, there are 3 cases of acceleration that you need to keep in mind. If an object is speeding up, speed is increasing, 10, 20, 30, this is called positive acceleration or just acceleration. That's called acceleration. Speed is increasing. If an object is slowing down, 30 to 20, 20 to 10, 10 to 0, like he's losing 10 meters per second every second, this is called deceleration or negative acceleration. All right. And finally, this is for the extended folks. If an object is moving and then it changes direction, if it's moving at 10 meters per second or kilometers per hour and it changes direction, it has the same speed. So same value. It is still accelerating. Why? Because the direction has changed. And if the direction changes, that means this velocity has changed. And if the velocity changes, but this is called acceleration. We do not calculate acceleration due to change in direction. We don't calculate it. It's not calculated. But we just need to recognize it. Like, hey, you're going in a circle, you're changing direction, moving from left to right. Are you accelerating? Yes, you are. Good. This is an extended question. So the question is, a ball is dropped from a tall building. It takes 3.2 seconds to reach the ground and falls with an acceleration of 10 meters per second squared. Calculate the speed that the ball hits the ground with. Here's the rule. Change in velocity over time. What have I given you? Speed is 3.2, time is 3.2, and the acceleration is 10. So what's the speed? Make it the subject. So change in velocity or speed is acceleration times time. The acceleration is 10, time is 3.2. This gives me 32 meters per second. So easy peasy. Some people say lemon squeezy. I don't know why, but I don't like it. Japanese. Let's talk about graphs. You have two types of graphs, distance time and speed time graphs. If you're given a distance time graph, the things you can simply say are A to B, you're moving at constant speed. Because the line is straight, it's going up, the distance is increasing. This is not speed, huh? This y-axis is not speed, this is just distance. And B to C, you're moving at constant. Wait, are you moving? Are you even moving from B to C? No, your distance is not changing. At 4 seconds, you're at 8 meters away from the start. At 5 seconds, you're still 8 meters away from the start. At 7 seconds, you're still 8 meters away from the start. You're not moving. You're at rest. Very good. The slope of this line, how steep or less steep this line is, represents the speed. So you can easily calculate speed using distance over time here. It's nothing special. Next. Very good. Moving on. Speed time graphs are a lot more nuanced and they've got a lot more detail. So from A to B, the speed is increasing, so it's acceleration. From B to C, the speed is not changing. This is not at rest this time around. The speed is not a changing. So this is moving at constant speed. Whereas C to D, it's a decelerating. The speed is decreasing. Okay. The slope of this line, like how steep the line is, up or down, represents the acceleration of the line. So the steeper the line is, the more you're accelerating. And the less steep the line is, the less you're accelerating. You're still accelerating, but at a lower value. If I were to compare the accelerations of AB and CD, yeah, sure, it's deceleration, but again, CD is decelerating faster or more than AB because it changes the same speed over a shorter time. Or you could simply say the line is steeper. Good. How do you calculate distance from a speed time graph? Very common question. You get the area under the graph. I know a lot of you would still default to, hey, Mister, is speed distance over time, so therefore distance equals speed times time. You are factually correct. But most of the time, it does not work when you want to calculate distance from a speed time graph. Because this rule only works if you're moving at constant speed. It only works if you're moving at constant speed. Here, the speed is not always constant. So it's area under the A graph. All right, very good. Let's try to solve this. Let's try to see. If you want the area of a triangle, what's this? It's half times base times height. This is the area that I'm talking about. If any of you are shy and you're not asking me questions here, this is the area we're talking about. This is the area of a triangle. So if I were to only ask you to calculate the area of AB, you would say half times base, which is 4, times height, which is 8. So half times 4 times 8. This would give you 16 meters. because the unit here is in meters. Very good. So go ahead and calculate the total distance. How to get the total distance? You can either split this into 3 shapes. So you have a triangle here, a rectangle here, and a triangle here. Or you can just get the entire area. I'm going to skip and use this entire area. I've already revised what the rule for a triangle is. That's half times base times height. And a rectangle is, that's just base times height. But what if I wanted this entire shape? This is a trapezium. And the way we calculate the area of a trapezium is base 1 plus base 2 over 2 times height. So base 1, which is 9, this entire base is 9, plus base 2, which is this thing over here from B to C. So from 4 to 7. 7 minus 4 is 3. So 9 plus 3 over 2. Times, what's the height? 8. 9 plus 3 over 2 times 8, which is 48 meters. All right. And how do we calculate average speed? This is like a follow-up question from the very beginning of this particular chapter and point. To get average speed, it's total distance over total time. What's the total distance? 48. What's the total time? 9. So 48 over 9 is 5.33333333. How many significant figures should I write my answers to in IGCSE? Well, just write it to 3. Just write it to 3 significant figures and give yourself a rest. 3 meters per second. Very nice. Now, as we already mentioned before, the slope of the line represents the acceleration. So the steeper the line is, the higher the acceleration. The less steep the line is, the lower the acceleration. A negative slope, yani negative acceleration. It means negative acceleration. That also means deceleration. And then, finally, oops. What if the line is curved? This is an extended part. I seem to have forgotten to add these, or they're not showing up. So, what if the line is curved? Then it's not constant. What's not constant? Acceleration. If the slope of the line is increasing, like it's getting steeper, we call this increasing acceleration. If the slope of the line is decreasing and it's getting less steep, this is called decreasing acceleration. If the slope of the line is increasing, but the line itself is going down, this is called deceleration because the speed is dropping, but this line is becoming steeper. And if the line is becoming steeper, the deceleration is increasing. You know? Over here, the deceleration is decreasing. So you can get a better mental idea of what that physically means. Increasing deceleration means you're pressing the brakes of your car or your bike slowly at first. So you're slowing down a bit, but then you realize like oh my God, I'm going to smash into that tree or wall or dog, and then you smash the brakes and you brake hard. Here, you brake hard initially. In decreasing deceleration means you brake hard initially, but then you realize, hey, you're braking too hard and you let the brakes go a bit. You're still braking. You're still slowing down, but you take a longer time. Yeah. Before I move on to forces, there was one question. So delta V is speed. Yes. Delta V in the previous equation for acceleration, change in velocity, delta V, the velocity is speed. So speed is acceleration times time. Forces. A force is a push or a pull. Nothing special here. But a force is a vector. to the extended focus, which means it has magnitude and direction. So the direction is going to be important. When you apply a force on an object, it could, change its shape, change its size. I can grab, I have a hat here somewhere. Yes, cap. I can take this object and I can fold it and I can squish it and I can bend it. So I can change its shape and size, no problem. I can take this ruler and I can bend it. I'm not going to break it up. But it can also change the speed and direction of motion of the object, the velocity of an object, essentially. A force cannot change mass. It's a very common multiple choice question. Force cannot change mass. Now, there are certain forces you need to recognize, at least in terms of name. There is air resistance. There is friction. These are both resisting forces. If you're moving through the air, it slows you down. If you're pushing an object on the surface, the roughness of the surface resists you. It's called friction. There is weight, which is the pull of gravity. We'll discuss this a bit more now. There is upthrust, which is the upward force of the water on the object. So it gets pushed up, it floats. There is tension, which is the name of the force in a thread or a rope or a cable. So if I have a rope or a thread like this, and I stretch it, the name of the force that's in the rope as it's being stretched is called tension. Ismu tension, that's all. It's just the name. And then there's normal contact. All right? Your hand is making contact with your phone. That's called normal contact. Okay? Good. Okay. Next. Let's talk about friction in a little bit more detail. What is friction? It's a resisting force. Tries to slow you down. It's the force between two surfaces, especially when it comes to solid objects, due to the roughness. The rougher the surface is, the greater the friction. You can decrease friction by lubricating the surface, like dropping some oil or water on the floor, or by making the surface smoother. Whenever there's friction, there's also heat that's produced, which is very common. Like if you're feeling cold and it's dead winter and you just rub your hands together, you feel warmer. Friction is also called drag. So if a car is moving through the air, air resistance is just another form of friction. Or if you're swimming in the water and the water is resisting you, that is called friction. You can call it drag, air resistance, friction, it all works. Now, a very important force is weight. Weight is defined as the force of gravity or the gravitational force on an object. Gravity always affects any object with mass. So this pen I'm holding and drawing with has mass. My phone has mass. My laptop, I'm not going to lift my laptop, has mass, right? Although I've dropped, oh God. Anyway, anybody who knows me knows how, aggressive I am with some of my technology. iPad throwing gang here. Anyone? Okay. Anyway, jokes aside. So it's the force of a gravity. You will never forget. You will never will. But what is mass? It's the amount of matter in an object. So mass is simply the amount of matter in an object. You calculate weight by using this equation. W equals mg. Weight is equal to mass times what's g? G is short for gravitational field strength. Gravitational field strength. It's how strong a planet's gravity is. We'll emphasize this more when we hit space physics as well. But the value of G on Earth is 9.8 newtons per kilogram. Now, one of the changes that wasn't mentioned in the early syllabus document, like the first document we saw, that was just a snapshot of the document, was this. They didn't mention it explicitly in the document, but they have changed it in the past papers. From now on, the value of G is going to be 9.8. As in every 1 kilogram is not going to have a weight of 10 newtons like we used to have. All of the mark schemes in the older past papers will have this as 10. That's fine. Anything before 2023, we'll have this as 10. From now on, it's 9.8, which rounds up to 10, so it doesn't matter. Next, how do you calculate resultant force? Simple. If two forces are in the same direction, 10 newtons and 20 newtons, their combined force or the resultant force is 30 newtons. If the forces are in opposite directions, so 10 newtons and 20 newtons to the left, you don't add them, you subtract them. So this will give you 10, sorry, why was I going to say 20? 10 newtons to the left. 20 minus 10 is 10 to the left. But then things get a bit more complicated when forces are not in the same direction. So if this is a 10 Newton force to the right, and this is another 10 Newton force to the right, at an angle of 90 degrees to each other, the resultant force is going to be something in between, and somewhere in between them. We don't know the exact values, but I can't just add them. Anybody who studies any kind of advanced math, trigonometry, and so on, will tell me that there's a method that you can use to calculate this. You can use the Pythagorean theorem, the Pythagoras theorems. Anyway, we're not going to calculate it here. We're going to draw what we call a vector triangle, or the head-to-tail method, to find the resultant force. Step one, and this is being very succinct and brief. You get your ruler and you draw this diagram to scale, which means that every 1 centimeters, let's say, is 1 newtons. So on my board, on my screen, I'm going to draw a 10 centimeter line to the right, because this represents this 10 newtons here. So 10 centimeter line to the right. Actually, let me use the line tool so it actually looks like a line. Whoop, here's 10 centimeters. This is to scale, at least to my scale, because it's on the screen. And then from the end of this line, you draw another 10 centimeter line at 90 degrees to here. So let's label these. This is a 10 Newton force to the right. This is 10 Newton force to the left. It's called head to tail. It's because you draw the head of this force attached to the tail of the next. That's why. So we just call it a triangle method or a vector triangle. Where is your resultant? The resultant is going to be the line that joins the start and the end of your diagram. This is your resultant. This is your resultant, R. If you've drawn this to scale, you can measure this with your ruler. You probably don't see me right now, but I've got my ruler on my screen, and that's 14 centimeters. Since I'm using a scale of 1 centimeter to 1 Newton, but this is a 14 Newton resultant force. What about the angle, the direction? Remember, vectors have to have direction. We almost always measure, unless the examiner tells me otherwise, the angle between the resultant line, resultant force, and the horizontal. This angle over here. What do you use? You use a protractor. Somebody has mysteriously removed, but I know the angle off the top of my head because, this is simple geometry. This is going to be 45 degrees. So my response to what's the direction is 45 degrees to the horizontal. 45 degrees to the horizontal. Right? Very good. Before I move on, questions? Okay, so no questions. Excellent. This is a good question. If the forces are not at 90 degrees, then what do you do? Let me clear all of this out, because that's a very good question. What if these two forces were at, and ignore this diagram for now, what if the forces that we're discussing were, let's say, a 10 Newton force to the right, and another 10 Newton force at an angle of your choosing, let's say 30 degrees. You follow the same steps. Step 1, you draw it to scale. Let's say 1 centimeter is 1 Newton. So you draw the first line. Always draw the easy ones, the horizontal lines, the vertical lines. So I'm going to draw a 10 centimeter line here. This might not fit on my screen, but I'll do my best. And then we draw this at an angle of 30. Now, what do I mean? Let me erase this. All right? I'm just drawing dotted lines so you know what I'm doing. If I put my protractor here, I will measure a 30-degree angle from the horizontal, and then from here, we draw the 10 centimeter line. There we go. So it's the exact same steps, Sarit. But what do? We measure this angle first. Finally, since we are drawing this to scale, this line is your resultant, and this is what you measure. I'll change the color to blue better. And oh gosh, this is going to be a big line, and it's about 18.4 centimeters. So the resultant is 18.4 newtons. And what's the angle? We measure this. This should be about, I'm really not sure, but let's say halfway between the two or something at 15 degrees. So we're going to say the direction is 15 degrees to the horizon. There we go. It will be 14. Like the previous example will be 14. If you tried using Pythagoras and it's not 14, it's 14.14 or something. Like 14.14, yes. It'll be 14. Let's talk about Newton's laws of motion. Newton's first law: an object at rest will remain at rest or in a constant state of motion unless acted on by an external resultant force, blah, 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 blah. I'm not going to memorize that. But what I want you to memorize is this. If an object is moving to the right and the resultant force acting on it is also to the right, this will accelerate. If an object is moving to the right, but the resultant is to the left, and I want you to understand what I mean by resultant. This means there are forward forces, there are backward forces, and after you subtract them, this is what's left. And in this case, the forward driving force is more than the resisting forces. Here, the resisting forces are more than the driving forces. This will decelerate. And if the object is moving to the right, but the force is sideways, the object will rotate, it will turn, it will change direction. So basically, if there is a force, the object accelerates in all of its meanings. Speed up, slow down, changes direction. But this is the most important part of it all. If the resultant force is 0, the forward and backward forces are equal, what will happen? If the object was initially at rest, meaning it's not moving, it stays at rest. It doesn't move. But if the object is moving, then the object moves at constant speed. The object moves at constant speed. Speed does not change. That's very important. This is the most important part. So if I tell you that the object is moving at constant speed, you can say that the resultant force is 0. If I tell you the resultant force is 0, it will move at constant speed. Both of these arguments are extremely important. Newton's second law, it's just F equals ma. Force equals mass times acceleration. However, there's one important thing here, besides the formula and using it. The force in this equation is the resultant force. It is not the driving force. It's not the resisting force. It's the resultant. So in an equation, for example, or as an example, I tell you, hey, here's a car. The driving force on that car is 100 newtons forward, but there is a resisting force of 10 newtons. And this car has a mass of, well, cars are supposed to be heavy, but let's just say 600 kilograms. Calculate the acceleration. So what do? F equals ma. So if I want the acceleration, a equals F over m. The force that you substitute here is not 100, and it's not 10. It's their difference. It's their resultant. So this car will barely accelerate, by the way. Like, I shouldn't have used the 110 as my forces, because that's nothing. Virtually nothing. 0.15 meters per second squared. That's your answer. But just off the top of my head, I like to drive slow, under the speed limit. Way under the speed limit. I mean, I'm driving so slow below the speed limit, I'm getting a ticket for moving slowly. I hate it when people do that, by the way, when I drive. Like, imagine I'm driving in the middle of the road, 5-lane street on a highway, and you're rushing, and then you've got this, I don't know what they're doing, watching YouTube or something, or playing Candy Crush on their phone, and they're driving slowly in the middle of the road. It's frustrating. Anyway, if you ever learn to drive, folks, you want to go slow, stick to the lane on the very far end, to the right example. Like, in our case, we drive to the right if we're slow. Anyway, I just remembered I need to get a driver's license soon. International driver's license, okay? Nothing. Anyway, this is literally a quick example. A force is given, a resultant force of 4,500 newtons is given, with a mass of 900. Calculate the acceleration. There is absolutely nothing special here. Acceleration is force over mass, with an actual proper value of force acting on this car so it can accelerate. This will give you an acceleration of 5 meters per second squared. Oops. Yeah. Finally, there are 2 cases of motion that you need to keep in mind and memorize. Case number 1, if an object is falling in a vacuum, there's no air resistance, you fall with a constant acceleration of 9.8 meters per second squared, which is the value of g. But if you're falling through the air, then there is air resistance acting on you. All right? The smaller the size of the object, the smaller the air resistance. And the larger the size of the object, the greater the air resistance, because that's one of 2 factors that affects air resistance. Size being the first. Second, we'll see in a bit. So the smaller the area, the cross-section area of the object, the smaller the value of the air resistance acting on. When an object is falling through air, it goes through 3 stages of motion. Stage 1, when it's just dropped, it falls with a constant acceleration, because there's only weight acting on it. But then stage 2, as it continues to fall, the weight is the same, but there's a little bit of air resistance. So as the air resistance, which I will call R, increases, the resultant force, which is called F, will decrease. I'll give you an example. If this is 100 and this is 10, the force is now 90. Before, the force pulling you down was 100. As the resultant force decreases, the acceleration decreases. Eventually, this continues to happen, by the way, gradually and eventually, the air resistance increases so much that it becomes equal to your weight. So the weight is now equal to air resistance. The resultant force is 0. They cancel each other out. And you fall with a constant speed. You fall with constant speed. We call this terminal velocity. So this is the second thing that affects air resistance. The faster you're moving, the greater the air resistance acting on you. If I draw a speed time graph of this motion, it will look like this. Accelerating, accelerating, but the acceleration decreases, 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 and then this is your terminal velocity. If you open that parachute, I don't want to call this stage 4 because you don't always open a parachute. Actually, if you're skydiving, you should always open your parachute at the end, but let's assume the parachute doesn't opens. Let's just say, oh, let's not go dark here. And you open your parachute for just the moment, and for the next few seconds after you open your parachute, the air resistance is now greater than your weight. You do not move upwards, you just slow down until you reach a new terminal velocity. Yeah. If an object is moving in a circle, the resultant force acting on the object must be towards the center of the circle. Always. So even if I'm saying you're moving at constant speed, you should be. But your velocity is changing. So your force, the resultant force acting on you, is towards the center of the circle. That's causing you to turn. Now, as the object turns and goes around the circle, if it either, number 1, moves too fast, or number 2, it has too much mass, or number 3, the circle's radius is too small, if any of these happen, the force that's pulling you towards the center will not be enough to keep you in a circle. In order to stay in a circle, you need a force to keep you, sorry, my nose is blocked a bit. In order to keep you in a circle, the force that you need should always be towards the center of the circle. Move too fast, this force will increase. Or if you're too heavy, like a big heavy truck, this force will increase. Or if you're trying to turn very sharp U-turn, this force will increase so much that your car, the friction, whatever force is trying to keep you there won't be able to keep you there. So you leave the circle. You will always leave the circle in a direction that is tangent to the circle at the point of release. So if my car actually is here, it shoots this way. If my car is here, it shoots this way, and so on. All right. Next, momentum. Momentum is quite simple. It's just mass times velocity. There's nothing special about it. Don't overthink it. Momentum is mass times velocity. A lot of people try to think too much about this. It's the product of man v. The unit's either kilogram meter per second or Newton second. You'll find out why it's Newton second in a bit. But you can use momentum to calculate force. The equation we use to calculate force when it comes to momentum is change in momentum over time. This also means that if I ask you to calculate change in momentum, this will be force times time. This will be force times time, because time goes up. Mr. Tubb, what do I use? F equals ma or change in momentum over time? Depends on the question. Like if the question literally gives you masses and velocities and momentum and such, just use that. If it gives you acceleration, just use the other. It's not that hard. Remember, folks, always hydrate. My biggest mistake in life. Actually, I have a lot of them. Always remember to hydrate. Finally, when it comes to momentum, there's one more quantity that's called impulse. Sorry. Impulse is literally defined as force times time. Impulse is literally defined as force times time. There's nothing else about it. But remember, on the previous page or slide, we defined force as change in momentum over time. But then when we made force times time a subject, it was equal to change in momentum. This means that force times time, which is impulse, is also equal to the change in momentum, which is basically momentum, assuming your initial momentum was 0. This is why the unit of measurement of impulse, which is Newton second, is also the same as the unit of measurement of momentum, which is kilogram meters per second, because they're just the product of mass and velocity, or the product of force and time. It's the same thing. Yeah. A very important law when it comes to momentum is the law of conservation of momentum. But yeah, let's solve this example really quick. A driver accelerates so at a force of 30 newtons, acts at a 900 kilogram car for 10 seconds. Calculate the impulse. Whenever you solve questions, I want you to do what I do. What do you, mister? I underline the numbers, and sometimes I even just write letters on top of these numbers to give me a hint. Like, what do I have? I have force, I have time, I have mass. What do I use for impulse? Well, I know that impulse is either force times time or change in momentum. I have force and time. So impulse is force times time. So 30 times 10, which is 300 ns. Then he wants the change in velocity due to the impulse. Now, do not go back and think of acceleration. What's the relationship between change in velocity and impulse? Well, I know that impulse is change in momentum, and momentum is mass times velocity. I have the impulse, and I have the mass. I do not have the velocity. That's what I want. So the velocity is the impulse divided by mass, which is 300 divided by 900. This will give you a recurring value of a 0.33333333. So 0.333 meters per second. Good. What's the law of conservation of momentum? It's defined as the total momentum of a closed or isolated system is always conserved, or total momentum before equals total momentum after. But in order for you to understand what I'm talking about, here's a quick non-numerical example. I'm playing pool or billiards. I hit the ball. The first ball is now moving with a velocity of 10 meters per second. I'm not going to calculate anything. This is just for the sake of the question. And this ball is stationary. This is before they hit each other. Bam! They hit each other. After the collision, both of the balls stick together and they roll together until they fall into the hole. And then I lose the game because I dropped the white ball as well, because I'm an idiot and I can't play pool to save my life. But how do we solve this kind of question? Like, how do we find out what is the velocity after they collided? This can only be solved if we calculate the momentum of each ball separately before the collision, and we add them. And we then calculate the total momentum of the balls after the collision. Like if they've stuck together, that's double the mass times velocity. And these two should be equal. Like the momentums of these balls before they collide should be equal to the momentums of the balls after they collide. This gives us the following example. Ball of mass A, 0.25. And here's my hint before I continue reading. If the question has not sketched this case that's in front of you, sketch it yourself. I don't want a detailed diagram. Just draw a quick sketch of before the collision and after the collision. Please. It helps a lot. Have a ball, 0.25 kilograms. What's next? Moving at 20 meters per second. That's great. Hits a stationary ball. So that's another ball that's not moving. I'm just going to write X so I remember it's not moving. of mass 0.025. It's a lot lighter. Maybe I could have drawn it smaller. After the collision, so that's before. After the collision, they stick together. Okay. So they're stuck together. So what's their mass? Oh, okay. If they're stuck together, we add their masses. So 0.25 plus 0.025. This gives me 0.275. We now have the mass of both of these balls together. And they're moving at a velocity that I don't know. This is before, and this is after. What's the momentum? First, calculate the momentum of the ball before the collision. Well, that's easy. Momentum of ball A is mass times velocity. That's A and that's B. 0.25, that's the mass, times velocity, which is 20. This gives us 0.25 times 20, which is 5 kilograms meter per second. Now, remember, total momentum before equals total momentum after. We're going to need this for the next part. Calculate the speed of the balls after the collision. Okay, so how do we solve this? Before equals after. What's the total momentum before? Well, this was 5 plus, this isn't moving. They're two separate objects. So this was 5, this is 0. There's nothing else before the collision equals. What's after? Mass times velocity. I have the mass, 0.275, but I do not have the velocity. I'll just label it as V. Find V. I'm sure you're all professional mathematicians by now, but you must be way better at math than me. So 5 divided by 0.275. This gives me 18.18181. That's a very curious number. 18.2 meters per second. That's momentum. Does anybody have questions about momentum? Nothing? We good? We good. Excellent. Let's move on. Hook. Hook's law, or as some of my students like to call Hookie's law, because he's such a hooky. No. Anyway, moving on. My God, that was so cringe. Before we talk about Hooke's law, let's define a few quantities. First, here's a spring. This is called the original length of the spring. Here's the spring after we attach the load, which is the force that's going to pull the spring. This is the total length of the spring, or the new length of the spring, or the stretched length of the spring. It has many names. All right. How do you calculate the extension? The extension is the difference between these two lengths. So I'm just going to call this L2 and L1. So it's L2 minus L1. Next, Hooke's law states the following. An object will always be, the extension, I almost defined Newton's laws. Brain fart moment. Extension is proportional to what? Extension is proportional to what? Load or force. When I say that they are directly proportional, this means that if the force increases, the extension increases, as long as the elastic limit is not crossed. So what's the elastic limit? It's the maximum force that the spring can handle and still go back to its original shape. So if you stretch a spring and let it goes back to its original length or shape. That's the elastic limit. Now, from Hooke's law, we have a very simple equation. It says that force is equal to spring constant times extension, F equals kx. The spring constant has a second name. We sometimes call it the stiffness of the spring, how stiff a spring is. If you want to calculate it, K is equal to F over X. Nothing special here. Just keep in mind the units. If the force is in newtons and X is in centimeters, for example, then it's newtons per centimeters or newtons per millimeters and so on. Very quickly, let's solve this example. Here's a graph. Use the graph to calculate the original length of the spring. Oh, wait, how do I know the original length? It's the length of the spring again. It's the length of the spring at a load of 0, like before it was stretched. So this is the length of the spring before it is stretched, 5. So it's 5 centimeters. So that's A. Next, the extension of the spring at 20 newtons. From 20, you go up the graph line, hit the graph line, and then you check what the length is. The value is not 8. Remember, you want the extension. The current length is 8. The original length is 5. So the extension is 3 centimeters. And this is better for the extended folks. What's the spring constant? Well, K equals F over X. I already have a value of F and X that's ready from the previous question. If the force is 20 newtons and the extension is 3 centimeters, we just got that. So 20 divided by 3 gives you 6.67 newtons per centimeters. Okay. Yeah. Pressure. This one's easy. If I get a sheet of paper, somebody's tried to write me this sheet of paper. If I get a sheet of paper and I punch it, nothing happens. But if I stab it, trust me, I have no homicidal tendencies, okay? If I stab it, what's going to happen? The pen is going to go through the paper. Why? What's the difference? Why? What's the difference? This very small tip, all right? This very small tip is a very small area. It's a very small area. And if the area is very small, the pressure of that force increases, allowing it to cut through objects. Allowing it to cut through objects. Okay? That's what we call pressure. It's the concentration of a force over a specific area. So it's simply defined as force per unit area. Simply force per unit area. Force over area. P equals F over A. If the unit of force is Newton and the unit of area is meter squared, the unit of pressure is Pascal. If you call it Newton per meter squared, that's fine. If you use Pascal, that's also fine. Some questions often use Newton per centimeter squared, but that is not going to be Pascal. What about in liquids? In a liquid, the pressure is not dependent on force on area. It depends on how deep you are in the liquid and how dense the liquid is. The greater the height of that liquid or depth, the reason we say depth and not height is because we measure it from the upper surface to the lower surface. So over here to here. Right now, it makes no difference, but it will in a bit. Just give me another slide. So the deeper the liquid is, the greater the pressure. That's cool. That makes sense. But what do you mean it's proportional to density? So if I have two measuring cylinders that are both filled to the same level, same height, but they're different liquids. This is water, let's say with the density of 1,000 kilograms per meter cubed. It's the density. And this is oil. Let's say it has a density of 700 kilograms per meter cubed, off the top of my head. Both of them have the same height, but both of them will not apply the same pressure. The water will apply more pressure at the base of its container or on the floor than the oil, because it's literally heavier. It's more dense. This is why when we calculate the pressure in a liquid, the equation is rho GH. The equation is rho GH, where rho is density. Remember? Earlier in the session, I told you this is going to be important. G is 9.8, and H is the depth. Keep in mind, a friendly reminder again, most questions in the mark schemes from 2022 and before that will have the value of G set to 10. So if you're practicing at home and you're solving past papers and it's not 9.8, it's 10, it's fine. But starting this year, the value of G is 9.8. Keep that in mind. Now, the final point I want to make here, which is very important, The pressure of a liquid is not affected by the area of the container. Give me a thin container, give me a thick container, it does not matter. The cross-sectional area does not matter. Give me a wave, like a container with the different cross-sectional area, give me a wavy container, it still doesn't matter. Wish I had a Stream Deck. Because this moment like needs a meme. It's like, it doesn't matter. It was like, well, I think it was John Cena, I think. But anyway. I'm sorry. Anyway, moving on. Last thing when it comes to pressure. The pressure underwater has an extra detail about it. When you go deeper, the deeper you are underwater, the more pressure acts on your body. You go and say, yeah, I know that, because there's obviously more water, there's more depth, that's great. Obviously, and it's harder to breathe, obviously, because there's more pressure acting on your body, and therefore, your lungs can. But anyway, the greater the pressure, but the pressure acting on you is not only due to the water. If the water applies a pressure of, let's say, 20,000 Pascal on you because of this height, the pressure acting on your body at this level is actually 120,000 Pascal. Why? Because the air itself also has pressure. We call this atmospheric pressure. Now, you don't memorize the value of this atmospheric pressure, but it's about 100,000 Pascal, or 1 times 10 to the power of 5 Pascal. So when you're underwater, the total pressure acting on your body is due to the sum of the atmospheric pressure and the liquid pressure. So both, not just one of them, both. Very good. Now, before I go on to moments, there were a couple of questions. Didn't you say that stiffness is the original? The stiffness is not the original position of the spring. Stiffness is just a constant. In springs, stiffness is just the constant. It just represents how tough the spring is. It's not the original position. I never said that. We call that the original length of the spring. And K equals F over X. That's when we calculate K, the spring constant or the stiffness. That's when we want to calculate this. Right? Nothing more. Absolutely, it does. All right, so it's just this. All right. Now, one more question. Does the atmospheric pressure apply to the pressure of liquids in the cylinders in the previous slide? Yes, it does. But the pressure we calculate here, is the pressure what? Due to what? The liquid. I have not calculated the atmospheric pressure. I did not include it. What I'm asking you to get is the liquid pressure. If I wanted the total pressure, I would say total pressure. I wouldn't say atmosphere. I wouldn't say liquid pressure. Yeah. We have a couple of more topics. Let's go through them very briefly and quickly because they're not too difficult. A moment. A moment is defined as the turning effect of a force. Nothing special here. So if you apply a force on an object and there's a pivot on said object, yani a fixed point on the object, applying a force on the object makes it rotate or turn. Take this ruler, I'll hold it from this end. If I apply a force on the other end, it will rotate or turn. That rotation, or the strength of that rotation, is called a moment. You calculate it by multiplying the force and the perpendicular distance from the pivot. So force times this distance over here. There are 2 directions when it comes to moments because a moment is a vector. If it rotates this way, we call it clockwise. If it rotates the other way, we call it anti-clockwise or anti-clockwise. Now, there's a when an object is completely balanced, we say it's in a state of equilibrium. Equilibrium means that the resultant force is 0. This means that the upward forces and downward forces acting on the object are equal, so they cancel each other out. And forces on the right and on the left, or pointing right and left, are equal. But an object, in order for it to be in equilibrium, also has to have a resultant moment of 0. This means that the clockwise moment needs to be equal to the anti-clockwise moment. So if you have a beam, like before, and you have a pivot here, and a force on this side, and a force on the other side, you have the clockwise with the anti-clockwise moments. When you multiply the force and distance, their moments have to be the same. If this is 10 newtons, for example, and 10 centimeters, and this is 5 newtons and 20 centimeters, obviously this diagram isn't to scale, and you calculate their individual moments. So it's say force times distance. So 10 times 10, this gives you 100 Newton centimeters. The anti-clockwise moment is 5 times 20, force times distance, which is also 100 Newton centimeters, but it's anti-clockwise. It will not rotate clock, it will not rotate anti-clock. يعني لا هيلف كده ولا هيلف كده. It won't rotate this way, it won't rotate that way. Capish? Sure, it's a capish. Next. Let's use moments to solve this example. In this question, he says the beam is in equilibrium. It's equilibrium, which means the clockwise moment equals anti-clockwise moment. F, and we're going to use both rules, by the way. F is the force of an unknown load. R is the force of the pivot on the beam. Using the information, calculate F and calculate R. Well, to calculate F, I'm going to need moments, because here, F is applying a clockwise moment, and the 100 is applying an anti-clockwise moment. R has no moment because it's passing through the pivot. If a force is acting through the pivot, it has 0 moment, please. So step 1, clockwise moment equals anti-clockwise moment. The clockwise moment is F times, what's its distance to the pivot? 0.2. The anti-clockwise moment is 100 times distance to the pivot is 0.5. This gives me a value of F of 100 times 0.5 divided by 0.2. 100 times 0.5 over 0.2. This gives me 250 newtons. That's fantastic. Now, this example, before I move on, this example should give you another hint when it comes to the relationship between force and distance when it comes to moments. The closer a force is to the pivot, the greater the value of that force. And the farther away an object is from the pivot, the smaller that force. Huh? Look at this, look at this. They're balanced, but this force is 250. It's more than 100 because it's closer. Think of that when you open and close your door. The easiest port to open or close your door is the very edge or tip of your door. You can use your finger to push and pull the door. Why? Because you're very far away from the pivot, so your moment is very large thanks to the distance, not thanks to the force. Next. What's center of gravity, or center of mass, as sometimes called? It's defined as a point where the weight of an object is considered to act. So we always assume that the weight acts through the center of the object, even though the weight actually pulls the entire object down from all parts, but we simply assume it's acting through the center. But if an object is not uniform, as in it doesn't have a constant thickness or something, it's non-uniform, the weight will act closer to the heavier side of the object. The weight's going to act on the heavier side of the object, closer to the heavier side. Now, there's no need to get the exact location, just a rough location is fine. Now, before we talk about stability, let's just do a quick review of how does an object fall in terms of forces. How does an object fall? Here's the center of mass. Here's the weight. When an object is tilted just a bit, and the center of mass is here, the edge of the object acts like a pivot. So this creates an anti-clockwise moment. So it goes back. So if you tilt an object a very small distance, it goes back. Very small distance, it goes back. If you tilt it a lot, however, when will it fall? When the force goes over the edge of the object, which creates a clockwise moment in this particular scenario, causing it to fall over. An object is more stable, as in it's harder to make it fall over, by making the center of mass lower. So the heavier the base of the object is, the more stable it is. That's great. And making the object wider. Because if the object is wider and lower, it's harder to make it fall. It's hard to make it flip over and fall. So it's more stable. Last but not least, let's talk about energy. Energy is a scalar quantity. And it's something we need to use every single day, all the time. Right now, I'm expending huge amounts of energy just talking and explaining things. And I'm using a lot of electricity to make my monitors work and my microphone work and everything else. And you know what? If I was feeling hot, I would turn on my air conditioner, which would consume even more energy. And after I'm done, I'll be hungry. So I'm going to need to eat because I need to recover my energy. So energy is something you need in order to do a lot of things. But energy has many different types, like kinetic energy, which is the energy of speed. The faster you're moving, the more kinetic energy you have. Gravitational energy, which is the energy of height or position. The higher an object is, the more gravitational potential energy it has. It's not doing anything with it, it's just stored because of how high it's going. Chemical energy, which is energy stored in food, in fuel, stuff that you burn, and batteries. That also works. Elastic energy, which is the energy stored in anything that is stretched, like a spring or a bow. You know, a bow, when you pull on the bowstring and it bends. Anything that you bend or compress or stretch, that's elastic or strain. Or a ball that you squish, as long as it's deformed, that's called strain. Internal energy or heat, obviously when you heat something. Nuclear energy, which is stored inside the nucleus of an atom. This is often released through one of two reactions, nuclear fission or nuclear fusion. And electrical energy or electric potential energy, right? But how do you transfer energy? How do you move energy from one place to another? Either we transfer it using waves, so light waves, sound waves, heat or infrared waves, all electromagnetic waves essentially. So think ultraviolet and everything else. All of these are just methods of transferring energy. Let's say light, sound, and heat are primary things, like heating. It's not just waves. So you could talk about heating through conduction or convection. We'll mention those in Unit 2. Doing work, which is just applying a force on an object, that's a method of transferring energy. And electric currents, you can transfer energy using electricity. This is why I often say physics is mostly a study of matter and energy in relation to mass and time, obviously, just matter and energy. There are two equations that you need to calculate, and this is extended only. Why do they not show up? When I was writing extended, part of me was thinking, hey, did I accidentally add an A here? So it's extended. I was such a cringe. I'm sorry. Sometimes I get these cringe jokes and I can't stop them. My brain works in mysterious ways. So anyway, please tell me I'm funny. Self-esteem and stuff. Anyway, calculating kinetic energy. How do we calculate this stuff? You calculate kinetic energy using this equation. Half times m times VA squared. Half times mass times velocity squared. So obviously, the faster an object is, the faster an object is, the more kinetic energy it has, right? Gravitational potential energy is calculated using mgh, so mass times 9.8 or 10 in the older mark schemes times height. So the greater the height of an object, the greater the gravitational potential energy of the object. Also, the greater the mass of the object, the more GPE it has. All right. But remember, Core students, year 9s, don't really calculate kinetic energy in GPE. That's why we're saying it's extended. Next. Energy cannot be created or destroyed. It's only changed from one form to another. Very important law. I'll just do one quick example. If you have a light bulb, what type of energy does it take in and what type of energy does it give out? It takes in electrical energy and it gives out what? Light and heat. If I give in 100 joules of electrical energy, the total amount of energy given out also has to be 100. Also has to be 100. So if I tell you, hey, you're giving out 80 joules of light, then you're also giving out 20 joules of heat. The total still has to be 100. Sometimes we represent this using what we call a Sankey diagram. It's nothing special. You've seen this several times in questions before, which is like this. Basically, we have 100 joules of electricity going in, which is then split into 80 joules of light and 20 joules of heat. All of this, like this diagram just shows you how it's split. The smaller or thinner the arrow, the less energy is split. And the thicker the arrow, the more energy is split. So if this is 100, this is about 80, this is about 20. It doesn't have to be to scale or anything. So if you take a look at this diagram, you should be easily able to tell what energy transformations are going on. This is an example for the extended students, again, because we're the ones who calculate gravitational potential energy and kinetic energy. The mass of a cyclist is 90 kilograms. This girl and her bike have a mass of 90 kilograms. She rides down without using brakes or pedaling, so it's just pure energy. What's her gravitational potential energy at the top? So yeah, GPE is mgh. So that's 90 times 9.8 times 10. So 90 times 9.8 times 10, which gives me 8,820 joules. Then, what's her speed? This is a very common question. So keep in mind, the gravitational potential energy at the top changes to kinetic energy at the bottom. Always. Assuming no energy losses. This is why I assume no friction or air resistance. So gravitational potential energy has changed to kinetic energy. But what's kinetic energy? It's half mv squared. What does he want? The speed. Don't let the word maximum confuse you. Don't let this confuse you. Maximum is just what's the final speed. So let's substitute. Kinetic energy is 8,820 because it's been changed from gravitational to kinetic. Half times m, which is 90 times v squared. Rearrange this. V squared is going to be equal to 8,820 divided by half of 90, which should be 45. And then we square root our answer to get v. So square root 8,820 divided by half of 90. This gives me a speed of 14 meters per second. We have three final equations that you need to memorize. Work, which is when you apply a force on an object and it moves a certain distance. You've given it energy. Work is calculated using force times distance, or energy is force times distance. I know it looks like the equation for moments, but the difference is that the distance is in the same direction as the force. It's not perpendicular. Same direction. So if I'm pushing an object forward, the distance you take is forward. If I'm lifting an object up, the distance you take is up. Power, or the height, yeah. Power is how fast you're transferring energy. It's just energy over time, or work over time. This is a very common equation because we use the same equation in Unit 2 in thermal physics when we calculate heat energy and I ask you, hey, how fast am I transferring the energy? Or here's the power and time, what's the energy? We use that a lot. And in electricity. So memorize this, very important. If I want to calculate energy and I've given you power and time, it's just power times time. And finally, remember when we were talking about how this light bulb takes in 100 joules of electricity, gives me 80 joules of light and 20 joules of heat? We say that this light bulb is 80% efficient. What does that mean? This means that it successfully converts 80% of the energy into useful energy. It successfully converts 80% of the energy to useful energy. So what do I mean? Efficiency is the useful output, so 80 joules. That's the useful stuff. The heat is considered wasted energy. I don't want heat, I just want light. So 80 joules divided by 100 joules times 100. So it's 80%. So 80% is useful. This means we've wasted 20%. So quick example. A crate is pushed 12 meters, that's a distance, across horizontal floor against a 30 Newton, that's a force, in 6 seconds, here's time. Against or with, I don't care. Calculate work. I know the equation. Work is force times distance. So that's 30 times 12, because that's force and distance. So 30 times 12, this gives me 360. 360 joules. Calculate the power developed in pushing the box. So power is energy or work over time. So that's 360 divided, what's the time again? 6 seconds, 6. So 360 over 6. This gives me 60 watts. The unit of measurement of energy is joules. The unit of measurement of energy of power, is watts. And I'm sure you've all seen the Harry Potter meme. If you're a Potterhead, there's like, you're a unit of power, Harry. And Harry responds, I'm a what? I love it. I love it. I'm not going to apologize for that cringe joke. I love it. Anyway, before I move on to power stations, there's a question. Is it possible for him to ask me to calculate inefficiency? No, because inefficiency isn't actually a term, but he could ask it directly. You could say how much or what percentage of the energy was wasted. Like he has to state it that way, but he can't just say what's inefficiency. But yeah, but he can ask you how much is wasted. So for Hanadi, what do you do in this case? You divide the useless or wasted energy divided by the total times 100. Is there any other question here? For those asking when will we be done? Right after power stations, so in a few minutes. Power stations are large facilities that we use to generate electrical energy because we live off of electricity. Like everything in our lives depends on electricity. So we need different methods of generating electricity. Different sources. There are renewable sources. They are sources that return when they're used up, like solar and wind and hydroelectric and waves and geothermal. All of these are renewable sources of energy. And non-renewable sources of energy, like coal, oil, and gas, these are fossil fuels. And nuclear energy, uranium that we use in nuclear fission. Nuclear fission is a process where you take a nucleus and you break it into smaller pieces, smaller nuclei, to release energy, which converts nuclear energy into heat and light. Changes nuclear energy into heat and light. In general, all of these have both advantages and disadvantages. Obviously, renewable sources' advantages are: one, they're renewable; two, almost all of them cause no pollution whatsoever. It's a very big advantage. Disadvantage is that they're not very reliable. Like you cannot generate electricity at night using a solar panel, for example. It's a big disadvantage. Okay. And they don't generate as much power as non-renewable, by the way. Non-renewable sources have very strong advantages. They produce large amounts of energy and they are reliable. Yani they work 24/7. Day, night, raining, or it's not raining, snowing, or it's not snowing. As long as I'm feeding it with fuel, it's generating electricity. Disadvantage is that they almost always cause a ton of pollution, depending on the type. So if it's air pollution, when you pollute the water, you've got a lot of waste that you throw into the ground. You've got nuclear waste that causes, cancer and ionization. It's very dangerous. So all of these are disadvantages. And obviously, they're non-renewable. They will eventually end. They do not come back when they're used up. Although, of the three fossil fuels, gas is the cleanest. It causes the least amount of pollution. And recently, a lot of scientists have been working very hard on nuclear fusion, which is a very clean source of nuclear energy. We use hydrogen and we fuse it together to form helium, and that also releases energy. It's a very difficult process, but it's very clean. But that's another story. Let's quickly go over the power stations and how they roughly work. You have a boiler in the chemical power station. You burn your fuel, which converts chemical to heat energy. The water turns to steam. The steam hits what we call a turbine, which is just a big fan. The turbine spins a generator. Remember the one with the coil, and it's between the poles of a magnet, and it cuts the field to generate electricity? Same thing. So it converts the kinetic energy of the turbine as it's spinning into electrical energy. The water then condenses. We send it back to the boiler, rinse and repeat. This works for oil and gas and coal and sometimes biofuels, by the way. Like when we have waste fuel from farms, stuff that you can burn, we just burn that and we can use it to generate electricity. Nuclear power stations work almost the same way, with the exception is that first we have a nuclear reactor where nuclear fission occurs. This produces heat, and the heat boils water. The water turns to steam. Steam hits a turbine. The turbine spins, and the generator spins, which generates electricity. So nuclear to heat in the reactor, kinetic to electrical in the turbine and generator. Hydroelectric power stations. We build a dam. We block off the flow of water, just like a beaver does, but better. When the water level starts to rise, because we've blocked the water, it now stores gravitational potential energy because it's higher than the rest of the river. When the water falls and falls down, whether it's from the top or from the bottom, it doesn't matter, we convert the gravitational to kinetic energy, which spins a turbine, and the turbine turns a generator, and the generator produces electricity. Geothermal is a very important one. It's just like the coal and nuclear power stations in terms of how they function. But we have the boiler underwater, and sometimes you don't put the boiler itself. We just have pipes underwater. We drop cold water down into the hot rocks that are underground. So we go to places that are naturally volcanic, and they have very hot rocks underground, not lava, obviously, but just hot enough to dump a lot of cold water down there. It boils, turns to steam. The steam goes up and turns a turbine and a generator. It's the same process, with the exception is that it's renewable. Geothermal energy is a renewable. The last three are very simple. Wind turbines just convert kinetic energy of the wind to electric. Wind hits this, it turns, we generate electricity. Done. Wave turbines are the same thing, but we use flowing water to turn the turbines or make them vibrate up and down, which convert kinetic to electrical energy right away. No other steps. Solar is even simpler. You've got light from the sun that hits these panels, and they immediately convert it to electrical energy. You'll notice that solar panels are the only method of generating electricity with no turbine and no generator, meaning there are no moving parts. It's purely a plate which produces electricity using light right away. And finally, hello? No, it's not. Okay. A very common question is this: is the sun the source of all of these types of energies? Well, yes and no. The sun is the source of coal and oil and gas and hydroelectric and wind energy and solar energy. The sun is not the source for, and this is what you need to memorize, of tidal energy, which is high tide and low tide. It's just like hydroelectric, but we use high tide and low tide. Of geothermal and nuclear energy. Why? Because nuclear energy uses uranium as fuel, which is just a metal that we dig from the ground. It does not come from the sun. Geothermal is just heat from the core of the earth that has heated certain parts of our crust. So does not rely on the sun. Tidal, which is high tide and low tide, the change in tides, is due to the moon. So it's unreliant on the sun. All of these come from the sun. Coal and oil came from living organisms that used to live millions of years ago. They were alive thanks to the sun, producing plants, and the animals would eat those plants and so on. Hydroelectric energy comes from the rain cycle. Water in the ocean is heated by the sun, forming clouds. The clouds rain. You get the idea. Wind comes from the sun. Because the sun heats up our atmosphere, the differences in atmospheric temperature from one region of the earth to the other causes it to move. And do I need to talk about solar energy? That's literally directly from the sun? I didn't think so. Thank you very much. We'll stop here today. That's Unit 1. I'll see you guys for the next revision sessions.